So thanks everybody for joining in. So before we start today, I just wanted to go over what we covered and see if there's anything that any questions you had based on our session yesterday. So we of course did the overview of the AVRS architecture system. Then we went through the Q-drone hardware and interfacing. And we did oh sorry, before that yeah, part two, sorry. The Quark software and the Q drone. So by now I think you guys are pretty used to MATLAB Simlink and Quark and how to set up and configure Quark for different targets, for local, for remote. Yeah, you guys are pretty used to that. We ran the basic communications demo. Then we did the Q-drone hardware and Quark interfacing, where we ran the camera check and I/O check, all through Symink and Quark. So we did that. Then in the last portion, we defined the rigid bodies. So we did the calibration. We went through the grounding square. We defined the rigid body. We adjusted the pivot point of the rigid body in motive to match the center of gravity of the drone, right? So that part was a little bit tedious, right? I'm not gonna lie. It's got a couple more steps, but we do that to ensure that the system is more stable. I definitely remember with our predecessor, the cue ball, which was a much kind of higher system. If you didn't define your center of gravity correctly, then it would wobble a lot. So it was stabilized, but it would wobble a lot, right? Because if you didn't define it as a center of gravity and define it as like the top of the object, then it wouldn't be as stable. So I mean that was very evident in that particular system. We had a couple of questions. I think we addressed most of them yesterday. One question that we had was whether or not we leveraged the GPU on the NVIDIA. So the answer is no. MATLAB Simulink and Quark, like I said yesterday, we don't leverage the GPU on there, the graphics board by any means, but you could, I mean, for the Q car, for example, you could leverage this, right? You could use but it would be using the Ubuntu OS, right? The NVIDIA like software, not using MATLAB Simulink and Quark, right? So I don't think we're quite there yet, but I mean, if we do end up with getting an example, then it would show up in our resources, right? Which you can update. So periodically we do updates on the resources zip. So so every so often I encourage you can check back in and rerun the batch file. So that's what we accomplished yesterday. Got quite a bit done. Everything that was scheduled to be done has been completed. Any questions based on what we did yesterday? Okay.
Mitch,
Yeah.
okay, when will we need the cameras to be calibrated again? Or
That's a good question. So camera calibration, it's hard to say exactly when. It depends lab by lab. Um, if your if your cameras are if okay, if you touch your cameras or move them or whatever, the lighting changes, you need to recalibrate. If your lab is pretty much has not changed, you might just need to recalibrate every 2-3 days.
every 2-3 days we have to
Maybe.
calibrate
Yeah, you might get away with just doing it once per week. But yeah, at least once per week.
once per week. Will there be any symptoms from which we will get the uh, hint that our cameras need calibration? For
Yeah. So
example,
if you don't calibrate for a long time and you load up your old files and you run it, then you might notice that the Q drone doesn't track as well.
okay, okay,
Yeah, you'll notice it's kind of like tracking, then stop the tracking, stuff like that. It'd be kind of intermittent. It won't be tracking continuously. So
okay.
that would be one of the symptoms of not calibrating enough, right? So I mean, I've had cases where the lab didn't calibrate for like a month, then we ran it, but that's what we noticed, that it wasn't tracking as well. So we did rerun the calibration um and stuff like that. So I mean, for you guys, because you're a print lab, and as long as another case like we had in New York City College of Technology, they had a temporary setup where they set up the AVRS, but they had a netting, but it was a temporary setup. It wasn't ideal, but they needed to get this done as soon as possible. And the net, every time they entered the net, it kind of touched one of the cameras. So that was really, really bad. We told them like, just you have to fix this, but just they didn't have a chance to do it for this temporary place. But that, again, that's problematic, right? But
Mhm.
if the lighting doesn't change, or the cameras don't change, stuff like that, if your environment doesn't change, you won't have to calibrate as often, but at least every week, I would encourage, right? If you've been away from it for a long time, you come back, I would encourage calibration. Now, I know yesterday it seemed like a whole bunch of steps, but when you do this, like it's just like anything, right? Like when you practice it, it's like second nature. It'll take you like no more than 7, 8 minutes. You do it really, really quickly. Because you know all the steps, right? The
Yeah.
wanting to take long, grounding plane takes a cinch. The pivot point took longer because it's the first time we did it, but after you do that a couple of times, then you just do it automatically, right? So it doesn't take that long.
Yeah. Thank you.
Yeah, that's a good question. So the other thing is to remember, so to that point, also before you do calibration, before you use anything with the cameras, make sure that they warm up for at least 15 minutes. So for
Yeah.
that, you have to load up the Motive software. Um, so if you haven't done so already, um, is the Motive software loaded?
Yeah, yeah. It's more than 30 minutes, far more than 30 minutes. It's good.
Great. Okay. Okay. So any other questions before we move on to today's session?
Does the reflectors need to be replaced regularly, or it is only once for all its life?
You never need to change the reflectors. The reflectors need to be unique for each one. You don't need to change them. But each object needs to have unique reflectors if you're defining different rigid bodies, like we discussed yesterday. And that guide will show you that we showed the PDF. It'll show you how to place all the different markers. Yeah. Anything else?
No.
Okay. All right. So today we're gonna run the hover test. So we define everything. So we're gonna go ahead and run the hover test, which involves basically configuring the different files for it, and we'll take you how to do the standard default flight, which is at 1 meter. We can bring it down a bit. Then we can show you how to change that height of the hover. Um, After that, we'll run the position control. Then after that, what we can do is maybe could maybe run the hardware test, where we might dip into the AVS application structure right after. So we can talk about this and talk a little bit about the add-ons that we have, and yeah, so that will basically be. So let's see how much time that takes, and after that, we can discuss other applications that you guys want to run during the question discussion period. Okay, so the position control example is very similar to the hover, but the position control example gives you more commands, stuff like that. So let's talk about these. So let's talk about that a bit. So I'm just going to move this here. Okay, so OptiTrack localization, we talked about that, how the cameras are connected to your ground station PC, and we define different rigid bodies. So, today maybe at the end, if you want, we can define your I don't know if your Qbot 3 has markers on it.
No. No
It
more.
doesn't, right? Okay, so we can't do that today, but if ever you want to do the leader follower, we don't have the application yet, so I mean, no worries, but I mean, in probably in a couple of months, we will be releasing it. And I mean, we have the files for the QDrone1 and QBot2E, which is like extremely similar, right? It's not that much work to change it, right? So I mean, but yeah, but if you want to do that, you can define markers on the QBot3. So let us know if you want to do that. I don't know if you have extra markers, but we can, you know, that you can purchase extra markers from to do that, and so we can talk about that if, to Raheem and stuff if you do want to do the leader follower later on. But again, we don't have the example yet, but you would need markers on the QBot3 and just place them in a unique configuration as per the PDF, right? The PDF shows the example configurations. So this is how we define all that, and this shows you basically the different axes that we define. So again, the motive, right? The Z points at the ground station, and then we do a rotation in order to have the Research Studio frame as shown here, right? So this is like the default frame that's used for autonomous vehicles. It's more standard. Then we did the visualization data, right? So we added your files, the calibration and the trackable file. We have the trackable ID, which was 1. So 1 was the stream ID, I believe, in Motive. So we did that, and then we looked to make sure that the system was being tracked properly. And we also did a check, right? We kind of brought the drone really high, and Raheem brought it to different extremities to see what was our workable what was our effective workspace, I guess? What was our trackable workspace? Because if you go far to the wall, then of course the cameras won't be able to see it, right? Again, you need at least 3 cameras to see the drone. Yeah. Sorry, I didn't want to show that. No marketing videos. No fun for us. All business. So here's the mission server. So the mission server, now you can open this. So if you go to your MATLAB in here, so this is my Quanser folder. So if you go to examples, autonomous vehicles, then you'll find different folders, right? So you want to go to QDrone2, and you'll see different examples here: position control, hardware tests, all that. But actually, for you guys, sorry, we're doing the hover test first. So that's where we're going to do all the different examples that we have. But in here, what we're going to do is we go to Setup, Autonomous Vehicle Research Studio, and do the hover test. So that is in step 13, which is the last step of this setup thing. So again, so this is in Quanser folder, Autonomous Vehicles Research Studio, and go to step 13, hover test, and then you'll see, first of all, the instructions are in, so know there's QDrone1 and QDrone2, so make sure you select the QDrone2. So it'll show you basically all the different checklists and how to set everything up here. Okay. And then you can, so inside QDrone2, you'll have 2 files. You'll have the mission control file and the PID flight controller file. That will be on the drone, and this one will be on the host machine. So I'm going to open up one of these, but this is basically how it looks like here. So the way you configure this is as follows, right? So you have the mission server, where you define your calibration and trackable or assets file, the motive file that you define, right? Motive or trackable file, the files mean the same thing. They're the files that define your rigid body. So you define that in your data server, and then this extracts. So then the next thing you want to check is after you define these variables, you want to make sure that it's tracking and that there's no joystick issues as well. I think actually even before the hover, we can do a quick joystick test as well to show you how to interface, how to do kind of a simple, how to get used to using the joystick. So this will show you whether or not there's any joystick issues and if it's tracking. You always want to make sure that is tracking is 1. The next thing you want to do is the flight controller. So the flight controller, what we'll do is we configure, again, the TCP/IP address of the drone, because this is going on the drone. When you're doing the hover test, then there's different switches, right? So you want to make sure that you first of all enable the speed controllers on the motors, and then there's two things here you need to use, right? There's two toggles. There's the disarm arm toggle, and there's a land takeoff toggle. So these are kind of shown here. So the arm disarm toggle are on your left. So you always want to make sure that when you start this out that that it's on disarm and also on land. So the takeoff land, the land button and the disarm button, they should be away from you, right? To make sure it's not active. And then you start the drone in that position. Then when you're ready to run it and you have the mission server running, you run the mission server on your host machine. So you define your calibration, your access file, you confirm it's tracking, you don't need to have joystick issues. Then you run the flight controller on the Q drone. So you make sure they're communicating, you get no errors. Once the beeping stops and everything's okay, then you can arm it using the joystick, and then you can do takeoff, and then you'll lift up to a certain height. And then when you want to land it, then you put the toggle back to land, and then you disarm it, and the models will stop automatically. It will give you a message saying, okay, the controller has ended, blah, blah, blah. It's just a warning message, but it always does that. So step 1 is again, run the mission server on the PC and then run the stabilizer control. Now, another note is you want to run each of these files in 2 separate MATLAB instances, right? So you run the MATLAB twice. So you have 2 MATLABs running. One of them you use the mission server, and the other one you run the PID stack, the stabilizer controller. So having each of these dynamic models running in 2 different instances makes sure that they're running in parallel in different processes and windows, and makes the performance better. So like I said here, basically, this is just what I talked about, right? So, yeah, so you arm it, and then the Q drone should go green, and then you go take off, and then it'll fly up. Then when you're ready to land, you land it and you disarm it. Best practices again is to make sure it's always tracking. The other thing is the Bluetooth dongle. You want to make sure that you disconnect the Bluetooth dongle and reconnect it to make sure you resume the connection. But before we do the hover test, we'll do a quick test on the joystick called the joystick demo that you guys can use. I think it's a good quick example that we can run. Um, the next thing is make sure the battery level doesn't go below 10.5 volts. Again, right, these batteries, you never want to make, you always want to make sure these batteries don't go too low of a voltage, right? Because you could damage the battery. So always make sure that it doesn't go below 10.5. Now, when you're running the hover test, you'll have what's called the FSM. So the finite state machine scope will open. So this shows you the different signals of the finite state machine. For example, when you arm it, when you take off, if you press the emergency stop, um, did it lose tracking? It also has a current state, so the state machine, we can maybe talk about that in the last part of the session when we take a deeper dive. Were there any joystick issues? Was the battery low? So there's all these different watchdogs, right? And actually, one thing I forgot to mention was that, yeah, right here. Can you see on the top left, right behind the arm disarm toggle?
Yeah.
There's a button called, there's a button there. The button is the emergency stop button. You can see it here. So if you look at your joystick, you'll see that button. So if anything happens, if this, the drone starts going unstable for whatever reason, you can press down that button. Any questions about the hover test?
Nope, I think we are fine. Good to go.
Just one question. This arm button, that's the same as with the drone itself because there is a arming button in the drone.
Sorry, I don't understand your question.
There is an arming button on the drone to enable disable the
Yeah,
models.
that enables the speed controllers. But it doesn't, arming it means arming it in the digital, because there's a manual switch, which is a hardware switch. If that's off, you can't arm it through the digital interface. This here sends a digital signal that enables the amplifier, right? Because the DAC on the QDrone 2 is connected to the amplifier, the speed controller, and it enables it using a digital signal. But if that switch, if the analog switch on the drone, if it's not enabled, then no matter what you do here, it's not going to drive it. So they're different. Yeah. Yeah, that's the master switch on the drone. It decides whether or not you can enable it at all, right? So it's the enable switch. This is the arm switch. So the arm switch is a digital thing, but if you have it, if the speed controllers are disabled, then they can't be armed at all. It doesn't matter what you do.
I got it. Thank you.
Yeah. Okay. Did you guys want to run this before we go to the position control? What's that?
Yeah, I think we can run it.
Okay. Sounds good. So before that, let's do a quick test on your joystick. So
Okay.
if you go to MATLAB and go to step 6 joystick,
Yeah.
because I just want to make sure. So before, again, like I said, under best practices, make sure, and it's kind of showed here, that you have the dongle and the joystick, right? So take this USB dongle and unplug it and then reconnect it, right? So that is something that you guys should do um, every time you haven't used the computer for a long time, because if the USB dongle is connected for a long time, the connection between the joystick and the dongle, it needs to be resumed. So you need to resume the connection by disconnecting the dongle and reconnecting it. So if you haven't used it like overnight, you definitely need to reconnect it.
Okay.
But I'll show you how to, like, it's easy to check, because basically before you fly the drone, you can move like the sticks around. If you don't get any response, then you know right away that, uh, you're not getting the. So you guys, I think, went through all the binding and stuff like that already, right? But this manual will show you that. So if ever the joystick is acting funny, then you can follow this guide to make sure that it's that the joystick is binding to the USB dongle properly. You can go through this procedure. But for now, I just want to go ahead and we'll go straight to the joystick visualization demo.
Mm.
Okay, so here is a joystick visualization demo. So you have the joystick FR Sky controller in here. So you can see that this is using the host game controller. It also shows a picture of the different buttons. So host game controller, again, these are Quark blocks that interface to the joystick, just like the Q car with the gamepad. You're using the same blocks, but in that case, the host game controller was configured to a different joystick, right? So it supports many different joysticks, and Yeah, so it basically does some signal conditioning, and that is what is used for, the if you want to command like the heading, the sway, the surge, and all that stuff. If there's any joystick issues, the arm, the disarm, and the emergency stop. So it gets all that data from using the Quark box from the joystick. So in here, what it's going to do is going to run a simple visualization. So let's run this first, then we'll go to the hover test. And yeah, that's the plan. So I will stop sharing my screen, and now you guys can go ahead and share your screen. So the joystick test won't run anything. It just runs, well, it'll run a visualization of a drone, and you kind of fly it around. It's just a simulation.
Okay.
That's great. You guys are following along, right? The CIMIC models as I was doing this?
Yeah.
Great, great.
So the dongle is connected, the light is green, and the joystick is also turned on. All the buttons are in the upward position, means disarmed and
Disarmed and
land.
land. Yeah.
Yeah.
Okay. So what you can do here, you can go to host game controller and make sure that it picked up your joystick.
Game controller.
Yeah, you're in. Go back in that block. Yeah,
Over
double
here.
click on host
Okay.
game controller.
Okay.
Yeah. So look at controller number 1. It says FR Sky Simulator. That
Yeah.
means it detected your joystick, so that's a good sign.
Okay.
Okay, excellent. Okay, now you can go back to the main part of your CIMIC model.
Yeah.
Okay, and click on, yeah, go ahead. You can run it. This will run on your Windows machine, so no configuration needed.
Okay.
Go to Quark, yeah. Okay, so as you can see, it says no joystick issues there.
Mm.
So, okay, yeah, are you doing it now, right? So yeah, great.
Mm. Okay, so it's
Yeah.
working.
So
Yeah,
this will
looks
give you a
like it.
feel of, it shows you the joystick is working, also gives you a feel of what toggles to use, right? To get kind of comfortable with the joystick commands before you do an actual flight.
Yeah. Okay.
So it's good for that purpose. It's good for,
Okay.
getting used to the joystick, but also testing the joystick on its own if you ever want to do that. You can also test it in the hover controller as well to make sure it's working.
Yeah. Okay.
Okay. Yeah, I just want to run that quickly so you guys know about it. It's could be handy. Yeah, click on stop, and now let's move on. You can close that, and let's go to the hover test.
Test.
Yeah, the last one. Remember, right? Everything is documented, right? So in each of these folders, you always have a PDF that shows you the procedure.
Into mission control, right?
Yeah, let's open that. So that is the one that is running on your Windows system.
Okay, so we have to open it into two separate instances, right?
That's correct. Yeah. So open this
Okay.
in one MATLAB, then open up another MATLAB. So you
So
want to
this
maybe make your MATLAB windows. You have 3 screens, right?
we already opened two MATLAB instances.
Can't we just use one computer?
One computer, it's one computer.
Okay.
And the second I have to open this one, right?
Yeah.
Drone stack.
Yeah,
Okay.
they renamed it. They call it Drone Stack PID.
Okay.
Yeah, Drone Stack PID. That's the flight controller that is on the drone.
Okay. Yeah, no. Yeah. Don't know. I should. Okay. So I think we have now to do the configuration, right?
That's correct, right? So remember now that the mission server. Now, where does the mission server run, right?
Mission server and the ground control PC.
Right, and the ground control PC is what is connected to OptiTrack and the joystick, right? So
Yeah.
it takes all that stuff. So it sends commands. It also sends the camera information. It streams it via the TCP/IP blocks to the drone, right? So that's what it does. So there's a couple of things you need to do, right? The first thing is you need to set up the calibration file and the motive / trackable file, right? So you can do that in your localization data server. You can see that block.
Okay. Localization data server.
You're looking at the wrong model. We're
Yeah.
looking at the ground station mission server. So you need to define your OptiTrack files.
Oh, okay. Okay. OptiTrack files for that.
So you see the OptiTrack icon in that block. If you go to your left,
Where is
it's localization data server. Jesus.
Sorry.
Okay.
Yeah. Okay. Equals
Yeah. So double click on that and then you select your two files.
documents, update track. Yeah. In the okay.
Okay. Click on OK.
Hmm.
And yeah, you can go back to that one there. Good. Now the other thing you can always do, you can always test to make sure your joystick is if you could zoom up on the first portion where the joystick is. So in here, it'll show you whether or not there's a joystick issue and if it's tracking, right? Those two yellow things. It also shows you the trigger displays. So this will display the toggles, right? So if it's armed or arm or disarmed, or if you're in a land takeoff position, it will display that in the trigger, right? So yeah. Now note that if it says joystick issue 0, it means there's no issues, but at the end of the day, if you haven't connected the dongle for a long time, it'll still say no joystick issues and you might have a joystick issue. Like you won't get any data. So if your drone like doesn't fly and you're doing the toggles or whatever, it means you need to like stop all the models, reconnect it, then confirm that you can get a response from the joystick.
Okay.
Yeah, so
I think we have to configure the communication stuff as well.
what's that?
Communication IP address.
For the PID. No, there's nothing you need to do there.
I think that was in the model. Model set. The model setting that was for the client. It's okay. I think it's local host. It should be.
Yeah, it's local. The submission server is running on your ground station. You don't need to set the IP address of that.
Okay. And code generation. Okay, it's
Yeah,
fine.
we're done with the mission server. You just need to define your OptiTrack files.
Okay, it's done. It's done.
Yeah. So now we have to go to your second controller, the one that's going on the drone. That's the one that you need to go to model settings and set the IP address.
Okay. Let's check. To the 2.10, right? So we have.
Yeah, so your first IP address is the ground station IP, and the second one is your drone. So I believe your
Okay.
ground station PC is 3.
IP. Yeah, .2.3. .2.3.
And okay.
.2.3.
Yeah, okay. And your drone is .2.10, right?
Yeah. It's
Okay.
it's okay. It's fine. Okay.
Yeah. Yeah, the target's already configured for QDrone 2.
Yeah.
Okay, you can save that.
Okay.
All right. Okay. Is your drone in the center of your workspace?
Yeah.
Yeah.
Okay, and the camera is facing away, right? So
Yes.
Yeah.
away from you. So
Yeah.
that's the fine. That's good. So it's facing away from you. It's in the center. If it wasn't in the center, that just means that when the controller runs, it wants to go to the origin first, right? Because what it'll do, it flies only with between the if it flies when X is 0 and Y is 0, and it just changes the height of the Z, right? So if your drone was like moved up to the side, it'll just kind of like move over to the origin, when you command it to go high.
Okay.
Okay, run the mission server.
So okay.
Yeah. And yeah, zoom up on there to make sure that you always want to make sure that it's tracking first, right? So I'm glad
Yeah.
you did the ping test. You do the ping test to make sure you can reach your drone. You changed your IP address you made sure the ground station IP was correct. The QDrone IP address is correct. Then you run the mission server in its own MATLAB instance. You make sure that the tracking is 1, right? So
Yeah.
it'll take, so right now it says 0. It takes a few minutes. Okay, so now it's saying 1. Okay, that's good. So that's your first indicator. Joystick issues says 0, so that's okay. Okay, so then you can run the QDrone stack PID and okay, so there. That is like the most important scope. So make sure you don't close this, right? Because this
Okay.
helps you monitor everything.
Okay.
It's also saved as a data file, but this is an important scope.
Okay.
Okay, so it's finished initializing. So it went from 1 to 0. Make sure so it's done. That you can just minimize, but leave the FSM scope open.
Fine. Fine.
Okay. Yeah, when you guys are ready, then if you're behind the net, okay, safety first, then go ahead and you can arm
Yeah.
the drone.
Okay. So I'm arming the drone. Okay.
Okay, so and then do the takeoff. But remember, if anything goes wrong,
Yeah. Yeah.
hit the stop, right?
Okay. Now take off.
Okay, good. So that is at 1 meter. When you guys are ready, you can put it on land.
Okay. Okay, done. Disarm.
And disarm. And then I believe the models stop automatically. At least the one on the mission server. Yeah, could you confirm that? And you probably got some messages saying that it finished.
Yeah, finish. It stopped on both instances. Okay.
Okay, so yeah, let's look at some of these scopes. Sure, we can look at the performance. So the performance is tracking. It's showing you the tracking from the measured data from OptiTrack and your desired data. Um, so in here, you can see that the X and the Y wasn't perfectly at the center, right? So when you ran it, which is fine, but so that's why it kind of went a little bit like this, when it first started, it kind of moved to the side to go to the origin, because that's your command, right? You commanded X and Y to oh, actually, I think what it did is it probably, yeah, what it did is it wasn't at the origin, so it just so it went to it yeah, no, I think whatever it starts, it actually it takes that as a reference point. So if you started not at the origin, it'll take the X and Y and latch onto those values. So it doesn't make it move to 0, 0. But then you see that once you've armed it, and once you do the takeoff, then the reference is in blue and it goes to 1, right, in your Z in the upper right corner. And then the yellow is your height measurement, right? So you can see there it's quite fast, the response, right? It's kind of like your classic, it kind of looks like a first order, second order response, right?
Yeah.
And then with stabilizing in the yaw, and the FSM scope, again, that's the finite state machine. Again, you got no joystick issues or battery issues. It showed you initializing arm. The takeoff here was 1, and then when you land it, it went there. But once you land it, then it stops the model, so you don't see when you disarmed it. No, it didn't fly too high, it didn't fly too low. But there's all these different watchdogs, right? That's what I'm showing you. You didn't hit the emergency stop. It didn't lose any tracking. There are no sensor issues. So that is what it's showing you, right? So I'm showing you this because if ever just for you to have the knowledge of how to best troubleshoot this if something does go wrong, right, then you can kind of look at this. Like, for example, if you didn't calibrate it for a long time, you're running it, it's kind of shaky and stuff like that. And then you see the tracking loss kind of like going like this is kind of noisy, but not 0, because tracking loss, if it's 0, that's good. Like we just ran it. That was a good test, it was stable. But if you haven't ran calibration, for example, for a long time, it might be running, but not a good performance, right? Because just kind of like losing tracking. So you might see that on that scope, right? So this is the key scope here.
Okay.
What'd you guys think? Was that easy to run, or
Yeah. Quite easy.
you felt comfortable?
Yeah.
Okay. Excellent. So there's a couple of things that you can adjust here. So let's try running it again. And now if you go to the mission server,
Missions are okay.
yeah, and move to the right, just scroll to the right. Yes. So the command generation, by default, when you're doing this test, the hover test, it goes to a predetermined height of 1. So you set the height at the home height constant in just your left there. Right, because it's on home mode, right? You're not using custom mode. No, keep zooming up on there.
Okay. Yeah. Going
Okay,
here.
so right now the command is on home mode, right? The home mode means it's using the lower portion of the switch. So when it's calculating the home pose in here, it's latching on to the current XY values, and then it commands a home height of 1. Now you could change the home height because we went up to 1 meter, as was evident when we ran that, but you could change this like 0.75 or 0.5. Now you can keep that, yeah, you can set to 0.8 if you want, whatever, doesn't matter.
Okay.
Sure, let's do that. And then what we'll do is we'll run it, and then we'll switch the, you can switch it to the custom mode. When you switch the command enable to custom mode, then the default position up above there,
Yeah.
you'll see it's a vector, right? It has 4 values.
Mm.
So that is the X, the Y, the Z, and the yaw.
Okay.
So you can see now that when you set to custom mode, the Z is set to 1 and X and Y are 0 and 0. So what we're going to do is we're going to run this again. We'll start in home mode. Then we'll flick the switch to custom mode. And because you're at 0.8, it'll probably jump up to 1 meter. And then you can try tuning the X and the Y. You can set X to like 0.5, negative 0.5, and see the drone kind of traveling in the XY
You are
plane.
Yeah. Yeah.
Yep.
Sorry, we lost you for a few seconds. Okay. So can we change the yaw as well? What do you think if we provide suppose 45 degrees, so it rotate as well?
We can try it, but I would recommend trying the X and the Y first.
Okay, fine.
Right.
So just we have to change the height, right?
But remember, when you're changing it in radians, it's in radians, right? So if you change the yaw, it's 9 degrees, right? So just so be careful, because if you command like 60.
No. Sorry, we actually lost you for a few seconds, so I'm just confirming what you want
No. What
us
I
to
want to
do.
do is you will run it in home mode, and it'll hover at 0.8 meters, right? And then we'll set the command enable to custom mode. So this will enable you to use this default position, right? The default position has more flexibility on the command you can give. So you can give an X command, a Y command, a Z command, and a yaw command. That's what this vector means, right? Right now, this vector is set up for the hover at 1 meter because the X is 0, the Y is 0, the Z is 1, and the yaw is 0. But we'll go here and then we'll change X or Y to like 0.5. Then we can switch it to negative 0.5, and we can look at the motions of the drone. And then what we'll do is we'll go back to the origin and we'll land it, and then we can look at the response.
Okay, so what I would suggest, actually, when the drone flies, we cannot hear you. So if you can tell us the mission, we will just do.
That's the mission, right? So move it. Yeah, no, I know it's not a quiet system, right? So it really wakes you up. It's the perfect system to run in the morning. So yeah, you can you can move X to like 0.5 or Y to 0.5, then move it back to negative 0.5, but don't go to 1 meter yet, right? Keep X and Y within 0.5, negative 0.5. Fly it a little bit, then make sure you go back to the home mode to bring it back to the origin, then land it. Does that make sense?
Mitch, actually, we lost you almost 2 minutes. Can you explain again?
Okay. So set this to custom mode.
Okay.
Can you hear me now?
Yeah.
And then you set your. Do you know what the default position means, right? The command for default position is X, Y, Z, and yaw.
Okay.
So what I'm recommending is just when you go, so fly this controller, go to custom mode, and then just change the value of X or Y to 0.5.
Okay.
Then you can switch it back. You can go to negative 0.5.
Okay.
And then you can switch it back to 0. And you can set the command enable back to home mode. And then you can land the drone.
Okay. Fine. I got you.
Does that make sense? So basically,
Yeah.
just start it in home at 0.8, then switch it to
Okay.
custom, and move it around X, Y, around the 0.5 meter space, right? Negative 0.5, 0.5, move it around a little bit, then move it back to home mode at the origin and land it. That's it.
Yeah, I think we can do that. We are ready. Okay.
All right. All right.
And
Good luck.
starting.
So yeah, start the mission server. So again, when you start on the mission server, always make sure it's tracking first, right?
Okay. Yeah, it's starting.
Okay, that's good. Okay, you can start your Q drone stack. Okay, it finished initializing, so when you're ready, you can arm it. Okay, you can go to custom mode and change the commands.
Okay.
Yeah, change Y.
Which one is X, which one is Y, and which one is Z? That's the first one is X, second Y, third Z. Then what of the angles? Although it is I know. The very first one.
Okay, this one.
Okay. Show me the angles. Each roll I knew.
No, there is no one.
You only?
X, Y, Z.
Okay, it is covering.
Yeah. So let me bring the other scope. Where is that? Yeah, over here we. Yeah.
Oh, great. Yeah, so you can, by the way, great job. That was a nice flight. So you can see here that when it initializes, the X and the Y, they latch on to whatever the starting value is of the Q drone. It uses that as its new reference point when you're in home mode. But when you go to custom mode, then it goes to X0 and Y0 and the height of 1. So you start out with an X of like negative 0.1, Y 0.1, and Z0. and then you moved it to 0.8 with the hover test. Then when you go to custom mode, it moved that to X at 0, Y at 0, and Z at 1 meter. And then you moved it on the X and Y at 0.5. And yeah, you got quite a nice response there. Yeah.
I have
And then
a
it shows you
question.
all,
I have a question. I have a question.
yeah.
Where are the angles? Roll, pitch, you?
The measured or commanded?
The command.
You can only command the
It's
yaw. You can't command
okay.
pitch, roll, and yaw.
Okay, we can only command X, Y, Z.
That's correct.
Okay.
Because when you're
So
commanding
how-
X, Y, Z, and yaw, the pitch and roll need to change. Those angles need to change in order to reach those
Yeah.
the X, Y, Z and roll position. You can't control all 6 degrees of freedom with only 4 rotors. Doesn't make any sense.
Okay.
Correct.
So you can only control
the
position X, Y, Z.
And yaw. So you
This
go
is the
X,
the
Y,
height
Z,
X and Y, but as you're doing X and Y and yaw and height, there's 4 things you could command. Then it changes the pitch and roll accordingly and the speeds of the rotors, right? So
Yeah.
if you try to change the pitch or the roll, I'm not saying you can't do it, but then that would be a totally different controller, because if you're changing the pitch and the roll, the drone's going to move,
Yeah, that's
right?
actually
So you
when
need to
the
have a limit of how much you're going to
Yeah.
do it, because this is a real system. In simulation, everything works, but in hardware, in real systems, you need to be more mindful of that and have and do some more stuff to the controller.
So now how can we modify the controller? Since this one is PID, so how can we use backstepping, sliding mode, and so on?
Yeah, I was gonna talk about that at the end of the session. I can show you basically how the controller looks like, explain what it is, and how you can modify it. So
Okay,
that is
then
going to be
another.
that is going to be in the training, but I don't want to talk about it. I mean, we can talk about it right now, but I wouldn't mind running the position control first.
Okay.
Is that okay?
just
Yes.
a quick question. Is it normal to have this fluctuation at the yaw?
it's actually zoomed version. It's you may consider it as
I
a
see.
yeah, so you can see 0.08 and
Okay, makes sense.
Yeah, it's
yeah, it's
pretty
noise.
small. The yaw will tend to do that, but that's pretty standard. I mean, that's 0.02 rads. That's pretty small.
Yeah.
Yeah, that's pretty default. I mean, it. I mean, you guys are there, right? In my mind, based on the response and what I saw on the camera feed, it looked quite good actually.
Yeah.
The flight, it looks quite stable. Do you guys agree or?
Yeah, we agree. We
Okay.
agree.
I mean, great job. I mean, this is a very nice flight. So I'm thinking we can run the position control
Okay.
and then we can run, I can show you a couple of hardware tests, and then we can talk about the PID controller and how you can modify it and more of the architecture of the system.
All right. I think we have nothing to explore in the drone stack, right? Should we close? Should I close it?
Yeah.
Okay.
We'll run a different controller now. It'll be very similar to this, but you have more commands.
All right. Now, yeah, that would be an example probably.
Position. Yes.
Yeah.
Position control. Okay. So drone stack and mission control again, 2 instances. Okay.
Yeah, so for that, I'll share my screen just for a minute, just to give you a overview of this. So position control is very, very similar. It's very, very similar to what you did in the hover test. So basically, you can see here that your mission server is almost identical.
Yeah.
The only difference is the command generation. So in the hover test, we did the home height, and then you switch to enable the custom mode, right? And you're able to get a constant, right? The constant you could set to whatever value you wanted, right? You guys can still hear me?
Yeah, we can hear you.
Okay.
We can hear you.
So I mean, so in this case, you have more control. So now you can give like square wave commands. So this will give, instead of you changing it manually, you could do square wave commands. So not only can you change it like a fixed position, like default position, like you did. So remember you had 0, 0, 1, 0, and you switch it to 0.5 or negative 0.5. In this case, you can go custom mode and enable a trajectory. And then when you go to pulse trajectories in here, right? So you set this to custom mode, and this we've already done, but what we'll do is we'll set trajectory enable to enable, and then you have different cases. So these different cases apply to different pulses about the different axes. So about the X, about the Y, and about the Z, and you could do the yaw. So that's what we'll do for the position control. After we run that, I'd like to talk about the different data saving capabilities, because this is something that will, at least I want to highlight, that it saves four data files, mission server and the flight controller combined. It saves data files based on your run. So it did that for the hover. You'll do that for position control. So I'll show you basically how to plot these commands, right? So that you can view your response after. So if ever you want to run a bunch of tests and then you want to, these are just MATLAB files, so you don't need Quark, you don't need this particular PC. You can run them on any computer with MATLAB, right? To view your results and your response, right? So you may want this if students want to use this in the report, for example, right? They might go in the lab, run a couple of tests, get their data files, put it on their USB key, and then do their lab report at home or whatever, or their thesis, whatever. So this will show you basically like you can plot basically your finite state machine scope, where it shows you, when you armed it, when the system was initialized, the takeoff, emergency stop. You can also do the tracking, right? So this is an example that we got from a client where they didn't set up their system correctly and the drone went unstable, for example, right? So in here, it's showing you the X and Y and Z, and it's also showing you, for example, that the tracking of OptiTrack was getting lost here, right? And then it went off course, and then we lost communication. So it can give you a lot of data. Okay, so yeah, I'll let you guys take it away. We can run the position control. Okay,
Sorry, it's configured.
great.
Okay.
Yeah, so do you guys understand? So okay, so when you're gonna run this, let's just so look at the mission server part 4, command generation.
Command generation. Okay.
Okay, so I'm just gonna kind of highlight what you need to do here is basically yeah, I would set the default position basically to 0.750.
Okay. 0.750. Okay.
Yeah, just so it's the same as the home height. So could you just move to the
I-
right a little bit? I want to show you the switch.
To the
Whoa,
right. Okay.
are you sure the default position was set correctly? Or?
I think
Oh,
so.
okay, it just looks weird. Yeah.
Yeah.
Yeah, so you're gonna start the controller as is, and then the home height will go to that will bring the drone up to 0.75. Then set it to custom mode.
Okay. Custom.
That will,
Correct.
yeah, when
Mhm.
it's in flight, not right now,
Okay, fine.
right?
Mhm.
Then you want to go to you want to enable the trajectories, right? So the orange switch, you're gonna put that to 1.
Mhm.
Then you can change the case, right? So there's 4 cases. There's 1 for the X, 2 for the Y, 3 for the Z, and 4 for the yaw.
Okay.
Now, the one note you need to, so this will change the pulse commands that are about the X, Y, and Z. So if you look at the waypoint trajectories,
Mhm. Okay, position matrix. Pause.
oh, they changed it.
Okay. Play
Oh,
pause.
I see. Okay. It looks like they changed it for whatever reason. That's fine.
Okay. So for 5 seconds, the first row will be the
Oh, I
position.
see. So it's just gonna, this is actually kind of neat. So it'll go through each of these waypoints.
Yeah.
So
Fine.
basically each of these waypoints are pre-programmed in here. So it'll go to each row here, and then it'll wait 5 seconds per location. So,
Okay.
so yeah, so it's actually, it's a bit more involved than just sending square wave commands, because that's,
Yeah. It's more flexible.
yeah, then it is actually, yeah, and it's more what you wouldn't do, right? Like setting
Yeah.
waypoints for drones are more common. So this is a more representative example.
Okay, fine. Great.
Okay, so in that case, then you just need to enable it, and that's it. You just let it run. So you don't need to change the case because that's it. So you just basically, you set trajectory enable to enable and just let it run its course.
Okay, fine. Fine.
And then when you're ready, you can always go back. You can always go back to disable, and that will bring it back to home, and then you land it.
All right, fine.
How is your battery level on your drone doing?
Battery level on the drone. It's how many minutes we need? Sorry.
You
4,
just
5,
need about a minute run.
9,
5-second
45.
Gs.
Sorry. 15.5. 15.5.
Oh yeah, I think we're fine.
Well, almost. Yeah, we are fine.
Yeah.
So we have
Yeah.
to configure the IP address. I think we did over here.
Yes.
Okay, so
You did that,
I'm
right?
ready.
Yeah.
Yeah, I did it. I'm ready.
Okay, you know what to do?
Yeah.
Okay, because I know you can't hear me, so I can send stuff through the chat. But remember, if anything goes wrong, so run. So go to enable to make it go through the waypoints, and then disable it to bring it back to home. Then
Fine.
land it. That's about it.
Okay.
And if anything goes wrong, you can always hit the e-stop switch.
Fine.
Cool. Okay, let's run that. And again, always go through the checks, right? Make sure the battery level. We check the battery level. It's healthy. And then you wait a couple of minutes for it to start tracking. Okay, tracking is set to 1.
Yeah.
Then you can run your PID stack.
All right. Yeah. I think you need some scopes as well. It's not. Okay, fine.
Okay, finish initializing. When you're ready, gentlemen, go ahead and arm it.
Okay. Armed.
Yeah,
Take off.
sure.
Okay. Just give us a minute because the battery cable is just hanging. That seems not safe. इसको नीचे वो कर ले.
Can we have 10-minute break?
You can go and print over here in the conference room.
Is it prayer time? Sorry.
Yeah, it's actually prayer time.
Oh, sorry about that. I do know about this, so if you guys, yeah, you can take a break if you want, definitely. No, definitely.
Center में ही रख दें. Okay. It's good. Okay. We just run. I think we need for 45 seconds. Okay. It will be done. Monitoring. Okay. No communication.
I think your joystick was on ARM when you started it, right?
Oh, sorry, it's unarmed. Yeah. Okay. Now I have to. Yeah.
No. You need to start the mission server first. See, you're going too fast here.
Actually, that was running and it's we cancel it and I will run it. Okay. So mission server is running.
Okay, make sure it's tracking.
Yeah. Tracking. It's let's confirm it.
Yes.
Okay. All right.
It's tracking it.
Yep. You guys can go ahead and arm it when you're ready and take off, and then go to custom mode, then go to enable trajectory, and then let it run its waypoints, and then bring it back to home and land it.
Okay. So take off. Okay. I hope we did it correctly.
You did perfectly. Yeah. So, yeah, let's look at the response. If you look at your pose performance and you zoom up on that, then by the way, if you guys want to pause here and for prayer time, we can start in 10 minutes, whatever you want. And we can look at this again. Up to you. I am mindful of this, right? So
What's the time? I think we can proceed. You pray and just come back. You can pray here.
No, we can't proceed. We have 10-minute break.
Okay, so we take 10-minute break if possible. Okay.
definitely, no problem. I'll be right here. So
All right.
okay.
Okay.
Okay. See you soon.
See you soon. Thank you very much, Mitch, for waiting. We can proceed.
Okay, sounds good. Okay, so if we look at the trajectory here, you could see basically that the x was a constant of -1, and then it switched back and forth between y commands, and it also commanded yaw. So the x remained at -1, then you commanded the y to -0.5, then 0.5, back and forth a bit, and it was also changing the yaw direction, right? At 0.5 rads. So that's why you were seeing it rotate, right, as it was in flight. Now, if you look back at your, and again, if you look at your finite state machine scope, you can see that everything went as planned. You got no errors, anything like that. It was a successful flight. Now, if
Yeah.
you look at your mission server, you could, of course, modify these waypoints, right?
Yeah.
So if you go to waypoint trajectories, this is what we went through, right? So yeah, it was pi divided by 6. So pi divided by 6 is what, 30 degrees or something, or 15.
Yeah. Pi is 180, so pi divided by 6 is 6 3s are 18, 30 degree.
Yeah. So it was going through 30 degrees and -30 degrees, and all that stuff. But you could change this ultimately, right? So you can change it so that it changes in the x as well. You could, if you want to add more waypoints, positions, then make sure you add it in the time trajectory as well, right? Because it waits for 5 seconds at each of these waypoints. So if you add waypoint locations, then you need to add it to the time vector as well, so that the vectors are the same size.
Okay.
Make sense?
Yeah, correct.
Now, this is one example. Now, what we have is actually, if you want, you can actually, if you don't want to use waypoints and you want to use the pulse commands that I showed you before, you could still do that. And there's actually, if you go to MATLAB, I want to show you, because you guys are, I would consider you guys more advanced than most, actually. So I can show you a bit more information here.
I'm in MATLAB.
Yeah. So go back to the QDrone 2 folder, just back one folder. Back one more to autonomous vehicles. Mission server snippets, the first folder.
Okay.
So if you go to position generator, this shows you some different options that you can use. So if ever you want to do like I said, the pulse trajectories that we talked about, it's still in here. So you can take this and you can add it to your mission server instead of using the waypoints. The waypoints are still here, by the way. The waypoints in the bottom left. The pulse commands that I showed you in my presentation are in the top left. There's also like a smooth box and a circular trajectory that you can use. So there's all these different options, right, to give you a couple of examples of different trajectories that you may want to give to your drone, right? The circular trajectory might be something you wanna try out, right? So stuff like that.
Yeah.
So that's an example of how you can modify the position commands, right? You could take that and you can maybe you could create your own folder and change your waypoints to using these kind of commands if you wanted.
Okay.
How would the software handle if the drone cannot reach to the target position?
If it can't reach, you mean if it's, what do you mean by can't reach?
There is, for example, an obstacle, or it is too fast to get to the point at the needed time.
Too fast would not likely happen because, I mean, this drone is quite fast. So, I mean, if your target, if your desired commanded position is like beyond your workspace, then it'll lose tracking. Is that what you mean?
Let's say that there is an obstacle is not registered in the software, and the drone hit that obstacle and cannot move further.
If it hit what? Sorry, I have a hard time hearing you.
Let's say that this hand is an obstacle not registered in the software as an object. Okay.
But it is defined as an object. I don't know what you mean.
Let's say that there is, for example, a wall that we did not register as a trackable object in the software.
Okay.
And it is there, and the drone is trying to reach beyond that wall. It will hit the wall, and it won't land.
I mean,
So what? How this?
if it does that, then there's nothing in the controller that knows there's a wall there. These are just example
It will
controllers.
keep-
If you want, but the way you can solve that is, I mean, that's it's a good question because that's like but in these examples, there's no detection of that, right? It doesn't know there's a wall there, but you could use the cameras to detect different objects, right? So you can use the cameras to detect objects that are nearby. So if that's how you would do it, but you would need to do that yourself, right? That would be something that's a bit more advanced because now you're dealing with object detection and obstacle avoidance, obstacle detection, right? So we have examples of that, for example, for ground vehicles, right? But yeah, and those are actually in the supplied material that you have. So you could take that kind of stuff and use it with the drone using the cameras. We had done yesterday, we had shown you how to interface to the cameras. We can show you other examples of the cameras, right? Like we have one example where actually if for example, if we are asking about how much what is your viewpoint with the cameras, right? There's one example that shows you in the read cameras. If we run that really quick, it'll show you that it uses the 3 CSI cameras in the front, the left, and the back, and it stitches them together plus the front, right? And that gives you a pretty good view of what's around the drone. So you could use these cameras in order to detect objects. Does that answer your question?
It answers part of it, but what if for any reason the drone cannot reach? Is there a timeout before it pauses and raises an error?
No, not for a wall. Not for a wall it
I
can't
see.
reach. I mean, no, I mean, there's a lot of different software, a lot of different watchdogs, software watchdogs. But yeah, there's a lot of different software watchdogs, but I mean, in that case, the drone just can't get past a wall. Is for these examples, there's I mean, your battery is going to get drained after a while. The battery level drops, then it'll eventually land because the battery level, once it drops, it lands automatically. So that would be one watchdog. But you could program another watchdog. I mean, it's not that hard to do. If your desired position is 1 meter, but it's stuck at 0.5 meters in the X, for example, because of some obstruction, then you could have a timer that's set off that's saying, okay, if I can't reach my desired position in 5 seconds, then land the drone. You know, that's easy to program. You could do that. But I mean,
Yes.
I think what you're getting at, you want something a bit more clever. So using the cameras to detect an object would be better because it's not reaction based, right? If you hit a wall and you can't move it past, you've already hit that wall. It's not ideal, right? You could easily program something that has a timer, like I said, right? Can't reach your desired position in 3 seconds, land the drone, right? That's fairly easy to do, right? Just look at the watchdogs we have and you could do that. But using the cameras to preemptively do that before you hit the wall would be the best approach.
Thank you. That's my answer that I'm looking for.
Okay, good question. Yeah. Anything else?
No.
Okay.
I have one question. Yesterday we saw there were some ports like SPI and I2C, some communication interfaces on the drone. Can we install ultrasonic sensor or some other sensors
Yeah.
on the drone as well?
Yeah, definitely. That's why we put that there. Yeah, you can definitely do that.
Great. Thank you.
Yeah, if you look at the user manual, the hardware guide that we showed yesterday, so under user manuals, QDrone 2, it gives you details of the pinouts of that board. Now, if you do need any more information on or help, don't hesitate to send me an email and we can try to provide you more information. But yeah, that's why we have that DAC with the different protocols so that you can add different sensors like that.
Thank you.
Yeah, definitely. Yeah. Okay. Yeah, close this. And how about we run the cameras example? We can go until we have until 4:30. Is that correct?
5:30, 5.
Okay. Okay, if we go to read cameras. Yeah, if you go to read cameras, let's run that really quickly. Yeah.
Okay.
So this one we've kind of ran the check before, but this runs, of course, on the drone because it's using the cameras. But this uses all the cameras in one model. So you have basically 3 video capture blocks that capture the image of the CSI cameras, and it's using this merge block, the same block that you saw with the Q card that used the 4 CSI cameras for full 360 degree. This will give you 270 degree for the most of it, and then it also shows you the front RealSense RGB camera. And it also give you the OmniVision optical flow camera as well. So so go ahead, let's configure that and run this really quickly.
Drone should be turned on. Give us 30 seconds. Actually, the drone was making noise, so we turned it off.
Yep.
So how can we control multiple quadrotos?
Can we just run this example first before we address other questions?
Okay. Okay. We wait
You
for
have to
the
wait a
drone
bit
to
until it logs on to the router, right?
Yeah.
Make sure there should be an IP address showing up on the LCD screen.
Yeah. Okay. So it's
Okay. Yeah, so this gives you a pretty good global view. You have that for that, and then the Intel Real Sense. So this gives you almost a full 360 degree view, and also gives you the depth measurement, right? Now the front is the easiest one to use for object detection, right? Because we did that with a Q car. So we use a depth measurement to detect objects when we were doing lane tracking, if you remember, right? You could take that algorithm, pop it in the drone to at least have that forward camera. But then at the end of the day, if you want to do something with the CSI cameras, you don't have a depth measurement on that, so it'd be a bit more tricky. But I'm showing you all the tools that you have, all the sensors and how you can interface to them, and the different resources we have that you can kind of use to do that kind of application to help you out. That's cool. I can see how you guys look like from another angle here. Okay. Great. So I just want to show you that in response to because I know we talked about that a bit yesterday, how much view you could get, and also it kind of talks about how you could use something like this with some algorithm to detect objects around the drone, right? So that's kind of what I'm getting at, that you have that capability. Okay, if there's no questions about that, we can click on stop.
Okay.
Okay. Yeah, you can close that one. I think we're done with that.
Okay.
Okay, so there's a few more examples here, such as, okay, we went through read a line. You can save, yeah, you can save videos as well. There's one more thing I want to show you in position control before I forget, and then we'll address the question about multiple drones, as well as hardware tests. And then I want to take a deeper dive for the PID controller, because we had that question, right? So first data logging, then multiple drones, then we can talk about PID, and hopefully maybe a bit of hardware tests, but we don't need to do hardware tests. We kind of covered last session. Double click on position control, and you'll look at there's a save data. So save data, there's two folders here. So if you click on the mission control, okay, great. So this is showing you the different runs that that you have done. So if you right click on the current folder menu bar next to name, you can add the date that was created. So if you right click on above the current folder, no, go to current, because I want to add the category of the inside current folder. It just says name. Right click.
Oh, yeah.
Right click next to name.
Okay.
And no, just add date modified. Don't use group. Yeah. Yeah,
Okay.
click on that. Yeah. Okay. So okay, this will show you when that file got created. So we can use the last one that we ran, I guess. So if you take that file, the first one that was created at 8:21 a.m., and you drag it to your workspace, to your command window. Yeah, you just need to load it in the command window.
Okay.
No, it's okay. You've done it once. It doesn't matter how you do it.
Yeah. Fine.
Okay. Okay, so go back to save data.
Okay.
And then you can go to drone stack PID. So that will give you, yeah, a set of 3 files. So make sure you use the 821. So you can take the first 3 and just drag it there. Yeah, no, just drag it in your command window. Okay, that's fine. Okay, so now you've loaded all the data. So it saves 4 log files as MET files, MATLAB data files. So then you can run these in a plotting script. So if you go to position control folder and go to scripts, then you can plot the different ones. So let's go plot data mission server first. And run that file. And then that will generate probably 3 figures or so.
Yeah, 3 figures.
So this is what I was going to show you. Like these are just plain MATLAB files, so you don't even need Symlink for this, right? And this will basically show you, I think figure 2 here. It'll show you basically, okay, the tracking signal was 1, so it was tracking all the way through your flight here. And then on figure 3, it shows you the X, the Y, the Z, and the yaw positions, right? So this is showing you the different commands that you gave, both the desired and the measured, and shows you how well it was tracking.
Yeah.
So that's what the mission server gives you, right? From the perspective of the mission server, now this here is giving you the data from the OptiTrack measurements. There's another one that will give you the estimated one on the drone, I believe. So let's look at, let's look at plot data commander. Okay, so this is a little bit lower level here. So this is okay, that's actually, so this one is important, figure 2 and figure 1. So figure 1, let's look at figure 1 first. We'll go one by one. So figure 1 is almost the same as what you saw before, right? But note that the difference here, it's estimated. So the one that we saw before was the direct measurement from OptiTrack, right? The direct measurement. But remember that we're using sensor fusion here on the drone. So the drone is using both IMUs and the OptiTrack data to try to estimate the most accurate position of the drone. That is what's being used in the controller, as we'll soon see. So that is what is giving you here. So it's a little bit different than what you saw on the drone. I mean, the differences are small, but there's a difference there about the results it's showing. Is that clear?
Yeah.
Okay. Now if you look at figure 2,
I think I need to make
so you can maximize that. Yeah, sure, that's fine. This is your famous finite state machine, right? So the finite state machine is showing you basically the status of the flight, right? So it's showing you all the different things. I think we covered this a couple times. So, but I just want to show you that it's the same thing as you saw in the scope, but it's saved. So if ever you do a few runs and you want to look at, the status of your flight or whatever, you can look at this. Okay, you can, let's go to figure 3. Yeah, this is showing the state machine. So the state machine, there's a state machine that is embedded in the mission server. So I'll show you where that is. It's basically just MATLAB code, and it shows you different states and stuff. But you would need to see the MATLAB code yourself and kind of dig through it if you want more information like this. Yeah, I mean, some people want to know, some people don't. So, but I'll show you where it is if you do want to know how the state machine works more. Okay, let's look at the last one. So the last one is showing you the reference thrust command. So this is lower level because the PID controller that we'll soon see is kind of a cascade PID controller. So it commands, you have X, Y, Z position, but that then gets translated to pitch, roll, yaw commands in order to reach X and Y, Z. Then it goes to, so that's what this is giving, right? The thrust command, the pitch command, the roll, and the yaw. So that's what I was saying back to the question of, can I control the pitch and the roll and the yaw? Well, no, because you need to adjust the pitch and the roll in order to reach that X and Y and Z position, right? So you adjust the thrust, the pitch, the roll to reach your X, Y, Z and yaw target, right? That's how this is done. So this is showing you the result of the first PID controller that we'll see very soon.
Yeah.
Make sense?
Yeah.
Okay. Let's run the other script. I think this was Commander, right?
Yeah. Commanded.
Okay, let's run the stabilizer. Hot data stabilizer. Okay, for this one, it's showing you a little bit more low level information here. Yeah, it's actually very low level. So this is showing you yeah, the reference torques that are given, right? So this is the result of the second PID controller that's lower level. So the first one from XYZ, you get pitch, roll, yaw, thrust. Those get then translated to force commands based on the thrust that we know, the system identification that we've done with the rotors on there. So this is giving you all the force commands you're giving, very, very low level. Yeah, but it's also giving you the watchdog timeout, communication issues, whether or not the model was stopped. It's also showing you the measured sample time as well as the computation time of the model. So the sample time is the sample time of your controller. So you set that to a certain level and it runs it at that level. But this is the measured, right? So showing you the measured sample time. And the red is your computation time of your model. So how much computation is it, right? For your model, right? So the bigger the model, the more complex the algorithm, the more the Simic model, the larger the computation time. The computation time will be less than the sample time because the sample time here is the control loop time. It's the time of the full loop that it's measuring. So it's going to be, it's measuring all the data from the IMU, from OptiTrack, from all that stuff. It's going through an algorithm. That's the computation time. Then it's applying that result and feeding that back, right? That's a full loop. So it's not just measuring sample time like an open loop DAC when you're just measuring a whole bunch of data, right? In more instrumentation kind of applications. This is the control loop cycle that it's measuring. So it's different.
Yeah.
Right? So it's easy to have a sample time of a megahertz or multiple kilohertz when you're just sampling a bunch of analog signals and not doing any closed loop, right? But this is control loop is a more accurate definition of what this is. Are there any questions about what this is showing?
Actually, the first three graph figures 1, 2, and 3 seems identical. I don't know if I'm missing
Yeah,
something.
it pretty much is. Yeah,
And
it pretty much is.
I'm feeling difficulty as well in understanding,
Like,
registering these figures.
honestly, I've never had a case where people needed to view this lower level, but I mean, this is only the only case that you would see this is just to make sure that you're not saturating something, right? Because
What I think that just the title and the legend of the X is also the X is legend that are changed, and
well,
rest of
okay,
the code is
okay. Figure 1 and figure 2 are the reference commands it's getting, right? From the stabilizer, because this is the lower level controller, right? So it's getting these reference port commands from the lower level PID. The first
okay.
one is unsaturated. The second one is saturated
Okay.
because you have the actuator limit. There's a torque limit of that, right?
Mm,
They are identical. You're correct because you're not saturating
fine.
the, which is good. They should be identical. That's what you want. If it's saturating, it means your controller, if you did, if you're doing your backstepping adaptive controller and it's
Mm,
going too high and there's this discrepancy between these two, then you'll know that, okay, I need to redesign my controller to lower the gains or do something because it's over actuating my system, right? I'm getting some cutoff there. So that's why it's showing you unsaturated command,
fine.
and then after that it's saturated. Yeah.
Fine. So, and the third one is generalized force command. Okay.
That one, I'll be honest with you, I think it's the same thing as figure 1. But
Yeah.
it's the one, it's the one, yeah, I need to look at that, but because
Total force.
this
Okay.
might be the one that was sent to the stabilizer, and the other ones are what was received by the stabilizer. So you could, but these again should be the same, like you see here.
What do you mean by stabilizer? The controller?
Again, yeah, there's
Okay.
the commander and there's a stabilizer. The commander is the first one, then the stabilizer. There's two. The controller is like a cascading PID controller. We're gonna get into that. When we get to that,
Okay.
this will make a bit more sense.
Fine. Fine. All right.
The last one is plotting the Q drone data.
Yeah.
So you go to your last script.
I think we have the how much script? 5. So sorry, script.
Yeah, plot data Q drone 2.
Okay.
No, plot. No, go back to
Okay.
plot dat Q
Listen.
drone 2, the script.
Okay. Lot of figures we.
So this is even lower level. So this is showing you again. So okay, the battery level, that's fine. The height, but this is like on the DAC, at the lower level, like at the DAC, almost the DAC level. But yeah, showing you optical flow data. The Actually, this is nice because it's showing you the IMU pose estimate.
Okay.
So yeah, this is showing you the first one as I believe the PWM commands to motor 1, 2, 3. So all the different motors, the motor telemetry. Figure 2 and figure 3 are the observer, the estimates of the orientation, the roll, pitch, yaw, the speed, and the acceleration. So these are directly from the onboard IMU on the drone. Remember, this is pretty low
Okay.
level, right? And then figure 4 is the optical flow data. So that is the optical flow from the downward facing OmniVision camera.
Mm.
Drone height is from the time of flight controller. So I believe, I'm pretty sure this might be the drone height from the time of flight ranging sensor, and then the battery level.
Uh, time of flight.
That's the height sensor.
Okay, height sensor.
Yeah, the ranging sensor. We tested that
Oh, yeah.
yesterday.
Yeah. Oh, correct.
Yeah, I
correct,
think
correct.
that's what that is. If it's not that, then
Yeah.
it's the height from OptiTrack. There's only
And
then it's
battery.
basically showing you the current that the electronics are drawing and the motor current.
Motor current in amp.
Yeah, in amp.
Yeah.
Low, it's low.
High. 40 amp.
Might not be amps.
Boris.
No, that's not amps. It's probably hang on here.
It should be amp. Usually, its current goes beyond 100 amps. And some big drones it goes beyond 300, 400
That
amps.
might be harmful for the battery or for the
No, these batteries are designed to withstand these huge load currents. Like for batteries.
The data sheet of the battery?
Yeah.
Oh, I see.
Can you please give me this battery? Anyone. This
I'm
battery,
just looking up what units.
this battery can give you 45 multiplied by 3.7, so it's almost 460. 160.
So guys, I'll show you where these files are. If you look at your QDrone, your QDrone stack PID.
Q drones. Sorry.
If you want to look at how the data is saved, open up. You can go back to your position control and open up
Okay.
QDrone stack PID.
Q drone. Okay. Yeah. Yeah.
Yeah, that's what it's showing you, right? So the motor current is going is directly from the Hill read.
Yeah.
And if you look at the Hill read, so Hill read here, you'll see that it has battery voltage, electronics current, and motor current. So if you double click on Hill read,
Mm.
and these are all analog measurements. And if you click on analog measurements, the dot, the button.
Okay. Analog.
Analog channels, click on the button.
Analog. Okay. Analog. Fine. Yeah, it's in amps.
So yeah, so you can see here motor current, electronics current, battery voltage shows you the units. Now you'll notice that there's another channel available here, analog input 0. That's your free channel on your DAC. So if ever you want to connect you know your analog sensor or another type of any kind of analog sensor, you could connect it here. You could drag this and have another input. That's where you read that additional sensor from, just to let you know.
Okay.
So it'd be easy to add. Yeah. So yeah, that was, we kind of highlighted all the information that you can view. So there's a lot you can, everything is logged. And as you know, every time you run it, it'll have another date stamp. So it'll automatically date stamp everything. So it won't overwrite the data files.
Okay.
Are there any questions about that? Yeah, actually, while you're on Hill Read, you can type, go to other channels. Oh,
Okay.
whoa.
Yeah, just give me a second. Yeah. What's happening? Why it's not closing? Okay. Hell read.
Yeah, if you go to other channels, dot, the button,
Okay.
other channels.
Other channels.
Bottom.
So this again shows you, you know, because they're using the gyroscope, the accelerometer on both IMUs, the optical flow, the RPM of the speed controllers, all that stuff, right? Showing you all the channels that are selected and used in that controller, right? So I'm just showing you the low level access that you have to the sensors, right? This uses pretty much everything. Okay. Yeah, click on cancel. Cancel. So the height estimate, if you go to your left, you'll see if you scroll down a bit. This is the ranging sensor, right? So the ranging sensor has its own separate block because it's not, because it's connected a bit differently, the time of flight. So the ranging sensor here is set up for that time of flight controller. So if you double click on that, you will see how that's set up. Because that's set up through the I2C interface. You can double click on it. Yeah, so it's giving you the ranging distance and all that stuff. So this is what you saw in the plot as the height estimate was using this. Okay. All right. Any questions about the data that we viewed and a little bit about the DAC information?
I think. I think. Yeah. So I was just wondering if these are the estimated, right? Not the measured one. These graph IMU attitude estimate.
Right.
So I don't know, but I'm feeling that there is a lot of noise, and if we have used some estimation or some filter, it shouldn't be there. What do you think? I may be wrong as well.
Yes, you're not wrong. It's just the noise is mostly on acceleration. The acceleration is very low, so that's natural.
Because, for example, if Kalman filter is used,
It
or
is
there
using a
is
Kalman filter, right? It's using a Kalman filter to estimate the
Oh.
position, which is smoother.
Okay.
This is giving you the raw estimate of the acceleration and the speed using the gyroscope and the orientation. This and that and OptiTrack, they're all used inside a Kalman filter.
These are the angular velocity and angular accelerations, right? Because in
Yeah.
radian per second, yeah.
Yeah, so if you maximize that and you zoom up, for example, in one portion of like from 40 to maybe from 60 to 70 seconds or 80 to 90 seconds, let's say, approximately.
Okay. 80 to 90 seconds.
Well, yeah, about right. So that's not noisy. It'll be kind of like moving a lot because it's constantly changing the orientation, right? But remember, this is used with the other one and the direct measurements, and then it uses that data to do the control. It doesn't use this to do the control by itself. It's giving you the raw information, and same thing with the speed. The speed here is your XYZ. So if you go, so if you go here and you zoom up on that, oh, you did already, yeah. So this, there's no like noise. It's just very fast commands, I guess, because it's speed, right? It's rads per second. It's speed.
Okay.
The accelerometers are notoriously always fairly noisy, but that's when you filter it out, right? Again, because when you're using the whole sensor fusion, yeah,
Yeah.
that, I mean, based on your run, the acceleration is just, that's just raw acceleration. Accelerometers always look like that in my experience. They're always very, very noisy, but
Yeah.
I mean, at the end of the day, we're using accelerometer, the gyroscope, we're using two IMUs with the optical flow data, and that's why when you look at the other plots, it's a lot more smooth, the pose, because it's using all of them together. It's not using raw acceleration for any of the controller part. It's just giving you the raw output of that, right? It's unfiltered or anything.
Yeah. Okay. Thank you.
Any other questions?
No.
Okay. All right. So did you guys want to talk about the PID controller right now?
Yes.
Okay. Yeah, I think this is a good time to talk about the PID.
And also how to modify the controller, how to
Yeah.
change the PID to backstep and slide mode.
I will give you guidelines on how to do that.
Okay.
Okay.
Okay, so let me show you a little bit about this. Okay. So here is the mission server, right? So in the mission server, we covered basically how you get the raw input commands from the host game controller, and then this gets transmitted to your trigger signals: arm, disarm, takeoff, land, emergency stop, any joystick issues. You also get the raw throttle and roll percentages. So if ever we have some examples that do like a manual flight where you're not using localization data. So that's when you can use this, or you can also use this, the stick commands from your joystick. If you want to use that to command a reference position like X, Y, Z, you could also do that. And that's in the snippets that we showed you, right? Like I said, the localization data is using an API, right? So the OptiTrack trackables block uses the Motive API in order to get your localization data. Right now, we're only using XYZ data, but note that, oh, and the rotation, right? So you're using the pitch roll yaw, and you're also detecting whether or not it's tracking, right? So that's the data we're using from OptiTrack, again, all on the mission server. Now in here, you're gonna get a convention correction, and this is what transfers the motor frame to the research studio frame. So again, the motor frame is that's like the raw frame of reference that you define when you put that grounding plane on your mat, on your floor, and define it that way. Then it does a 90-degree rotation. That's where this is done in order to have the frame of reference to be the autonomous vehicle one. We covered this part already. Okay, so now let's talk about the controller. So the flight controller has the commander portion and the stabilizer portion. So the first one is you receive data. All this is all the data that's received from your mission server. So it receives the OptiTrack, the measured OptiTrack position that was measured by the mission server. It's streamed via TCP/IP to the drone. So it takes the XYZ pitch roll yaw that were measured from OptiTrack, and it also gets the commands from the mission server, whatever the commands are, the position commands. This is using the estimate pose using onboard IMUs and OptiTrack. So this is what's basically doing the estimation and converting that to the horizon frame. Then it's going to the commander. So the commander is your first kind of controller. That is giving you basically your thrust and your pitch, roll, yaw commands, right? So it's transmitting now. So after you've estimated the measured, then it'll take your commanded X, Y, Z, and yaw commands, and it'll transmit that. It'll transmit that inside into throttle and pitch, roll, yaw commands. And also does the finite state machine. So the commander has the finite state machine is implemented in the commander. Then we have the PID control that will actually stabilize the drone. So that's a bit lower level. And then we have the physical plant. The physical plant is your hardware interface to the drone. We looked a bit about that when we looked at the Hill Read. In here, we'll talk a bit more about how it converts the generalized force commands that you've calculated into PWM commands.
Hmm.
Now you can monitor the tracking performance, and we've done that using the IF pose tracking, but that's where you can find the scope, right? It opens up automatically when you open up your PID stack, but it's inside that the subsystem here. And here is your finite state machine. So you can also, your finite state machine, whoa. Yeah, so your finite state machine is viewed all here. So we can look a bit more at this, but basically your finite state machine looks at whether or not it's tracking, the triggers, the signal checks, the battery level, all that kind of stuff, and it goes through a state machine based on those measurements. It goes through every state, right? So, initialization state, arm state, takeoff, any errors, land, disarm, stuff like that. If you press emergency stop, those all go to different states at the end of the day. That's basically what it is, and this is how it's implemented. Now here's how the control architecture works. So you get your estimated pose error. So by pose error, I mean you have a desired X, Y, Z, and yaw command. So X, Y, Z, and psi. I'm using the psi variable here to define yaw. So you have your commanded and you have your measured pose. So the pose is being measured through, again, through that the complementary filters, right? Using the two IMU sensors and OptiTrack, it estimates the X, Y, Z, and yaw of the drone. And then you have the command from the mission server. It takes the difference of those, and that's your error. This will go to the commander. PID, we call it a PIV controller. We call it a PIV controller because it's feeding back the rate. It's not feeding back the rate of the error. Just small little difference. It's basically it's almost the same as a PID controller, but it's not taking the derivative of the error. It's just feeding back the velocity of it, right? So it's a slight difference. The commander will give you the desired pitch torque, roll torque, thrust, and yaw torque. This will then convert it to generalized thrust, roll, pitch, and yaw commands. So based on your position, rate, acceleration, your attitude estimate, it goes to your first stabilizer, which will give you the pitch rate, roll rate, yaw rate, which goes to your second stabilizer. So it's actually a three-step process, right? So once you have your thrust and your torque commands, then it can send your torque commands to your PWM. So let's look at the first one. So here's your pose error. The pose error goes through your basic PID controller here. But again, we call it a PIV controller because, as you note, it's getting the error of the position, and then it's feeding back the rate as well into the negative terminal because it's negative feedback. So you're getting that. These are the PI gains, the PID gains that we use. We're saturating. Whoa. and then we're saturating those commands, and we're mapping the command, the XYZ. We're just switching it so it's in the convention of the thrust, the roll, the pitch, and the yaw. So we're just changing the convention of command to match that more generalized command. So basically, at the end of the day, guys, what this is doing is converting the X, Y, Z, and yaw error into pitch, roll, thrust, and yaw rates. Right, so you get X goes to desired pitch, Y goes to desired roll, height goes to desired thrust, yaw goes to desired yaw rate. Once you get that, then it goes to your second stabilizer controller, which is 2 loops, right? So the roll pitch, so based on now that you have your roll and your pitch angles, your thrust is for your height, and then you have your the thrust gets fed directly here, and then you have your roll and your pitch going here, and your yaw rate, and that gets into the second controller, right? Which so this will compute the pitch, roll, and yaw rates. The pitch and roll yaw rates, the reference rates go inside the second controller, which will give you torque commands. The torque commands are then sent to your QDrone2 DAC. So based on your torque commands, these torque commands here, they are converted into PWM commands based on the motor matrix that we've derived, right? The motor parameters. So based on the thrust parameters of the motors themselves, the rotors. It's a data sheet that we supply with the manual, with the documentation. So the PWM commands are, based on percentages, and then we have, and that gets sent in here. So this is fairly low level, but the motor commands are also use their own state machine, and then you use the flight controller output here. We have our own block that does the flight controller to make it a bit easier, and that gets applied directly to the PWM inputs in the hill right. We also monitor the status of the battery and whether or not it's armed, if the e-stop was pressed, and we send that to the LED. The LEDs, we command the LEDs on the drone using this. It's a lot to take in, I know. It's a big controller. But yeah, this conforms the force to motor command percentages, and this applies the PWM commands to the speed controllers. Those are the two main things here. Again, this is not something everybody needs to know about because we supply all these examples with this given, right? But I want you to at least know what is going on here. So it's not like it's not a question mark, it's not unknowns. At least you know from a high level what it's doing. If you need to modify this, which is maybe unlikely, because if you're doing a more high level controller, you probably don't need to dig this deep. But if you do, you know where it is. You can gotta have a good global understanding, and then you can look at the details in that. And if you have further questions, you can always email us. But I kind of just showing you a bit of bits and pieces of how everything together. But the most important thing is the big picture. We covered how it's reading different sensors, right? So the Hill read interface goes directly to the sensors, and you can. We saw how it's basically monitoring the gyroscope, accelerometers, and all that kind of stuff. We also looked at the height sensor. So the height sensor was a tensor time of flight sensor, which has its own block. Same with optical flow. Optical flow is from the Hill read, but in here it's showing you it's passing this through a filter, and it's showing you the optical flow measurement, like the raw measurements. And it's also showing you the average estimates. So the minimum, the average, the mean, and the max. So a bit of background of optical flow is it's basically it's using a reference point, right? So as you have a reference object like that, or it could be the floor, if the if the if the drone moves in by a motion of a distance of dx in the x direction and dy in the y direction, then it can use the downward facing camera based on a reference position. It can detect the motion it does in the xy, right? So it's another on top of the IMU sensors and OptiTrack, you can use optical flow to estimate where the drone is in the XY space. So you have optical flow for XY, you have time of flight for the height, and these are all on board, plus you have two IMUs, right? So you have a lot of sensors on the actual drone and different sensors that you can use for more elaborate sensor fusion and stuff like that. And at the end of the day, you also have the OptiTrack cameras as your kind of your reference direct measurement, right? That you know. Uh, so that's why the system is really great, because you can do all kinds of research, observer design, and you can always validate that your observer is working by comparing it with the OptiTrack measurements. So if you go ahead and design something with your time of flight and using optical flow, and you derive a totally new observer, you know where all the blocks are, you could define that, but you can compare that with your optical flow, or with your OptiTrack. So here is how it does the attitude estimate using IMU. So I'm using IMU 0. So you're getting right here, you're getting the gyroscope data. So it's so that's roll, pitch, yaw rates, and then X, Y, Z linear accelerations. So you have six vectors here, right? You go through a low pass filter to filter out some of the noise. Then is going to the complementary filter estimates to estimate where the pitch and roll angles are. And there's some documentation on how we use complementary filters inside the concept review. So if you look at examples, SDCS, QCAR, actually, if you look at SDCS here, and you look at skill activities, hang on, I'm trying to, sorry, go to Quanser, concept reviews. If you go to concept reviews and you want to learn more about the sensor fusion we do using complementary filters, go to the sensor fusion concept review. This will show you how we're using the complementary filter design. But yeah, so this will estimate based on your gyroscope and accelerations. It will take that data. So you have the roll acceleration, you have the pitch acceleration of the body. It takes that to estimate where the pitch and roll angles are. And then the yaw angle is from the gyroscope. So you're taking the integral of that. Yeah, we already covered how we're getting the pitch and roll angles from the accelerometer. So basically it's kind of like this, right? So you have the slower direct measurement from the accelerometer, and then you have the faster signal measurement, the derivative of x from the gyro. So the faster gyro angle rate measurements and the slower angle measurements from the accelerations. This is what gives you, well, and for the improving the yaw angle estimation, it's using your gyro and also the yaw angle measurement from OptiTrack. So this is to improve the yaw angle estimation. And this is for the pitch and roll. For the pitch and roll, you use basically the gyro, the accelerometer, and this one you're using the gyro and OptiTrack. So you're using a slower measurement and a faster measurement, you're using that. That's basically how the complementary filters work, right? So you're using two different sensors, one fast, one slow, and that gives you a pretty good estimate of where the vehicle is. Okay, so let's look at this more. So the QDrone2 stack. So like I said, in here we have the communication, and then this is where, if you look at your first block here, then this is where you're improving the yaw estimate, right? Using that complementary filter. And then you're converting that into, so you have the different frames here is the inertial frame, the body frame, and the horizon frame. So the body frame is the frame of on the drone. And then when you convert it to horizon frame, again, if you want to look at more information about different frames, then look at the frames of reference in here. This will show you a little bit more information about the inertial frame, the body frame, and the horizon frame. So the horizon frame in here, the initial frame is your base frame here, and then you have your body frame and the horizon frame. The horizon frame will be where you don't have pitch and roll. I think it's those are fixed. So you have, so in your horizon frame, you'll have Z, X, and Y and yaw, right? So you have X, Y, Z, and yaw. So in the horizon frame, you have X, Y, Z, yaw. You don't have pitch and roll. And this is basically what I showed you in here. So this is basically how you improve the rate estimate using the complementary filter. Then in here, the commander is where you have your state machine implemented. So if you want to know how the state machine works, you can dig in this. And then this is your first PIV controller. This is the first PIV controller that we covered, right? Where it's taking your X, Y, Z, and yaw angles, right? So the error, based on your desired and measured, is going through this PID controller, and it's converting the X into a desired pitch rotation, converting the Y error into a desired roll rotation, the height into a desired thrust, and the yaw into a desired yaw rate. So this is basically your commander. So it's taking the XYZ, XYZ and yaw and converts it to other commands for the lower level controller, which is pitch, roll, yaw, rate, and thrust. Then when you go to your second controller here, the stabilizer, then this is where you have your two other PID, the first one and the second one. This is in the stabilizer level, right? So the first one is a commander where you transfer commands from XYZ roll into pitch, roll, yaw, rate, and thrust. And then in here, it'll take the pitch and roll angles and calculate the pitch and roll rates. You already have the yaw rate in here, and this will command, and the second PID controller will give you your torque commands. The torque commands are then sent out and converted into PWM commands. So that is all. So now the question is, if you want to modify this, then first of all, you have to say, okay, you may want to keep the lower level PID controller as is for now and change the way you change your pose error into pitch and roll. If you want to do that, then all you need to do is say, okay, I don't want to use this PIV controller. You take the pose error, and then you do your own controller. Or if you want to modify the lower level PID controller, then you can do the same thing, right? So if you want to have a better estimate of where the roll and pitch angle are based on the pitch, roll, yaw and thrust commands, and you can delete this and add your own, right? So you just take this, design your own controller. So if you make a structural change, of course, you got to go back to monitor and tune and rebuild your controller. But if you tune stuff on the fly, like gains, right, like we did, right, when you're changing the manual switch around, stuff like that, you don't need to rebuild. Does that help answer? I know this is a lot to take in, but I mean, I think once you guys look at it yourself, it's very well documented. So it's very, I mean, there's 3 controllers, but each one does a specific thing. So if you just follow along with the documentation and based on our discussion here, I hope that you guys can kind of navigate. And at the end of the day, if you guys do have any questions, you can always email me, and we can help you out. If you're trying to do some kind of, like you mentioned, backstepping or whatever kind of other controller, and you're struggling a bit, send us an email and we'll try to help you out.
Okay. I have 2 questions right now.
Yeah.
You can answer. So the first one is that for the height, we have the downward facing camera, right? For height measurement. No, for the
No.
sidewise. That was for
Yeah.
the sidewise. You mentioned many times the time of flight sensor. So there is some ranging sensor as well.
Yeah.
Which is facing down. Okay. The second, you explored the IMU estimation block, and there we found just a complementary filter for sensor fusion, and also for the filtering probably. But we didn't saw a Kalman filter as you claimed that we are using that for the filtering
I
estimation.
was incorrect. It's using complementary filter. It's not using Kalman.
Okay, so probably if we use Kalman filter, we may reduce that noise in this estimation.
Maybe, but I think at the end of the day, there wasn't that much noise.
Okay,
But yeah, I'm not doubting it. Kalman filter is it's been used a lot through history. It's the most
Yeah.
popular observer.
Yeah. Thank you.
If you want to use Kalman filtering, then you would go inside here. Inside your horizon frame conversion estimation,
Yeah.
you would go here. And instead of using complementary filters, you could change this to use Kalman.
Okay.
We actually even have, if you go to Quark, sorry, if you go to simulation library browser, because I've used Kalman filter before, but under the Quark targets menu, we have continuous, and we have some stuff here, extended Kalman filter and stuff like that. You may want to look at that. Because we have used Kalman filter and I've used it in some other device, but you can implement it using that. You may not need it because it supports the MATLAB block, or if you do, Quark supports most blocks in Simulink as long as the blocks are supported by MATLAB code and SimEncoder, you should have no issues. But just to show you, we have this as well.
That's great.
Yeah. So just might save you time. Might make it easier to implement your Kalman filter using this block.
Yeah.
Any other questions?
The keyboard, you did not say anything about keyboard.
Because I didn't know you guys had one here. I was under the impression you only had one QDrone 2.
We have actually 2 keyboards and 2 Q drones.
Right, but when we did the pre-commissioning, there was only one QDrone 2.
Oh,
I found out about this yesterday.
Oh, okay. In the pre-commissioning, I was present, but actually, yeah, you are right. He just presented one
I had
drone.
no idea about this.
Okay.
But like I said, I mean, You have Qbot 3, right?
Yeah, keyboard 3, correct.
Okay, so if you go to Quanser
Mm.
and you go to examples, autonomous vehicles,
Sponsor examples,
Autonomous
autonomous vehicles. Yes.
you have Qbot 3 examples here. I guess hardware
Yeah.
test and Simlink.
Yeah, right.
But you also have it. Do you have the resources for the Qbot 3?
Resources, think- I don't know whether we have or not.
Okay, I'll send you that.
2 or 3?
Two drones, two keyboards. Keyboard 3, yeah.
3.
Yeah, it's keyboard 3. Keyboard 2.
Also, I have another question. How can we control two drones? We have two drones here. So how can we control them at the same time? Leader,
Okay.
follower, frame.
Do you have what?
How can we control two drones in leader follower framework?
We have a swarm example that should help you out.
Okay.
Are you guys all grad students?
Yeah, we have one postdoc. I have masters. He's probably master student, and then he's
Undergrad.
undergrad.
Because I want to share the resources of Qbot 3 with you.
Okay.
Then how can we
Okay.
control the two keyboards with one quadrature as a leader?
Can I just finish? Who can I share the Qbot 3 resources with?
You can share. Yeah, with me.
Yeah, share with you.
Please keep Mr. Rahim and CC as well, or you can share with him directly.
Okay. Okay, I'll do that separately. Now, okay, no problem. So I'll send you that so you have the full Qbot 3 resources, so you can run the Qbot 3 on your own time, and we can always let me know how that goes. Okay. Now, if you go to Quanser examples, go to autonomous vehicles,
Okay.
multi-vehicle,
Okay, multi-vehicle.
and if you go to leader follower,
Okay.
you'll see that if you go to waypoints, we don't yet have the example for QDrone 2 or Qbot 3. That's going to be coming up later. So when that comes up, I'll let you guys know, and you guys could run that.
Okay.
Now, back to the question you had about running multiple drones together. Now, this is not quite leader follower, but this is, we don't have leader follower for two drones, but we do have a swarm example that's running multiple drones. So if you open up this, then this is from another folder. So this is the mission server swarm. So for mission server, you could actually run this because you have QDrone 2s, but again, I just found out about it yesterday. But let me show you this. So mission server is what you've always done, right? So in mission server, you would basically go in here and it's the same deal as always, right? So you set up your joystick and you set up your OptiTrack data. So you would set up your files in here, but note the difference here is you have two trackable IDs. You have one and you have two. So, so you will need to define your second QDrone 2, right?
Yeah.
In OptiTrack.
Yeah. Rigid body.
Yeah, rigid body. Yeah, exactly. So,
Yeah.
you don't actually need to recalibrate. You can open up your old calibration file in Motive, and it'll already know about your first rigid body. And then if you bring in your second drone and then define that as a rigid body with stream ID 2, then you'll have two drones being able to track. Does that make sense so far?
Yeah. Yeah.
Now, when you look at this, hold on. Just want to see where you can see if it's tracking. Oh. Yeah, so in here it'll show you whether or not vehicle 1 is tracking and whether or not vehicle 2 is tracking. So you can add, I would add display box to this, but okay, and then you have your PID. The PID stack is exactly the same as before. There's no difference here. So you go in here, and the only difference in here is you can run this through a batch file. I mean, the thing is, you need to have, so you run this as, you have a batch file in here. So 2Q drones, and then you have this here. Where, so I just clicked on edit there, and you set the IP address of your first drone, which would be, for you guys, it would be 10. And then your second drone, whatever that is, might be 12. This would be 3. And then you would save that, and you can run this example here, launch all Q drones. But you need to build each one separately first. So I'll show you some instructions here of how to run it. But it's the same deal as before. Where you go in code generation and you set your IP address exactly like you did before. Right, so in here I got 5, but you set this to 3, and then set this to 10, and yeah, I mean it's the same type of deal. If you want, you don't necessarily need to run the batch file. To be honest, with 2 drones, what you can do is actually have one 2 drone stack for, you could call this like QDrone 2 drone stack PID, QDrone 1, and another one called QDrone stack PID, QDrone 2. set the IP address of each drone in each one of these and run the mission server and do them all manually like you did before. I personally prefer doing that because I have more control over the scopes. When you run the batch file will run all the core controllers by themselves, right? It's good, but you can't monitor the data as much and you don't have as much control. But if you have a lot of drones, like if you're doing a 5 swarm, you can't do 5 here. But if you have like a lot of drones, then the batch file is nice. But if you have 2 drones, I would actually advise you guys to run it manually this way. If you ever but the first thing you need to do when you want to run a swarm example like this would your other drone, you need to change the markers because I think the markers on each are the same, right? So what you would need to do first is just your second drone, just make sure you change the marker so that's unique, right? So you want to look back at your, again, if we go back to Quanser user manuals and you go to your actually, if you go to, sorry, if you go to setup autonomous vehicles and you go to rigid bodies, then this shows you the different markers, right? So here are the markers you could put on the Qbot 3. And here are the different markers that you could use for QDrone 2. So look at whichever one you have defined on this one. And then for your other one, you can just change this around. Then you open up motive, you drag the second rigid body in, define that, save it as a new motive file because you need to save a new file because now you have 2 drones. Then in mission server, you'll be able to detect each drone. So you'll get XYZ pitch roll yaw of each drone. And then you run the controller files. And here it'll show you basically shows you the instructions and shows you how to position everything. Any questions about this?
No.
Based on, I mean, you guys are pretty savvy with how you're running this, so I don't think you would have too many issues running that. But if you do end up trying to run this and you're at a sticking point, then I can help you out, right? So don't be shy. If you have any hesitation, if you want to run the swarm with 2 drones, are you planning on doing this anytime soon or?
Do you have any plan to implement some
Yes.
soon?
Yes, soon.
Okay.
Well, first make sure you're used to running a single drone, and then you can, like I showed you here, and then what's that?
Yeah, correct.
Why?
Yeah.
No, I just wondering why you're laughing.
No, actually, it seems a bit.
On the tough side.
What's that?
It is a bit on the tough side to control the 1 drone, so how about 2?
Yeah.
It's a bit what?
Yeah.
I didn't hear you.
He says that it's quite challenging to fully control or understand a single drone. So going towards swarm, it's a big task.
Yeah. Okay, that's what I thought you were saying.
Yeah.
Yeah. I mean, make sure you're used to. Yeah, I mean, make sure you're used to 1 drone and stuff like that. But try this out. It's fully documented. It's not that bad to run. But if you want, then let me know if you're having any challenges of running this. Send us an email and we can help you out, right? If you need more information on how to run it, if you want us, maybe we could take a video or we could set up, we could do whatever, right? So
Sure.
Yeah. If you ever need to run this and you're having challenges, we can always set up a short, like 30-minute or 1 hour, 30-minute session or something. But probably not this week. And next week I'll be away. So, but first run the Q drone 1, the Q drone 2 on its own. Run through the controls. Make sure you're very comfortable with that. The hardware test. You know, look through the resources, and then you can progress to the swarm.
Okay.
Does that sound good or?
Sounds good.
That sounds good.
Okay. All right. Any other questions?
Yes. Control of heterogeneous system of Q drones and Q bots.
I just talked about that. I showed you the examples already that we have, and we don't have that released yet.
Okay.
Like I just showed that. Sorry, it's just, if you go again to examples, autonomous vehicles, multi-vehicle, we have leader follower, we have waypoints, we have mission server, but it's only right now, it's only for Qbot 2 and Q drone, right? We don't have Q drone 2 and Qbot 3 yet. It hasn't been released, but it will, and this will show you basically how to do control of multiple vehicles together. So we're planning on releasing this. I'm not too sure when, but I'll find out the timeline.
Okay.
Yeah. It's definitely possible because we've already done it with the Q drone 1 and Qbot 2 a lot. Like we ran it a lot, but it's just for Q drone 2 and Qbot 3, we don't have that particular configuration yet. It's in our to-do list.
All right.
Yeah, sorry about that. Are there any other questions?
Very clear. Excuse me.
Yeah.
What will happen if we use this simulation for the heterogeneous of Qbot 2 and implement it to what we have? Yani, is there difficulty?
No, it's not that bad. You want to take these examples and modify them for your case?
Yeah, and try to implement it in our hardware.
Sorry.
Yeah.
Yeah. Yeah, if you want to do that on your own, let's say I go to waypoints, and so you have basically for your case, you don't need these, right? You're just dealing with the mission server, Qbot 2, Q drone in here. So if you take this, this would not actually change at all. This is basically the same file because these are just rigid bodies. So you would not need to change this too much because these are just detecting the rigid bodies. Now the Qbot 2 leader and these would have to change, right? So for example, if you take this and you want to change this for the Qbot 3, then I would just change the commander to Qbot 3 leader. And then you need to go in here and you go to your stabilizer. Because you're not using Qbot 2E, you would need to go to Qbot 2E here and change this to Qbot 3. Right, that's the basis of it, right? So after you've done this, then I just need to double check that all the inputs are okay.
Qbot 3 have Raspberry Pi 4, right? In that case, target file probably.
Yeah. So in here, you need to change this to so you need to change your system target file to this one here. So this is the Qbot 3.
Yeah.
And so this would be Qbot 3 plant and Qbot 3 DAC. So that would be for this. And then you would do a similar thing for the drone. So for the drone, it's a bit more heavy though, because in here, the controller for the Qdrone 2 is different than the Qdrone 1. It's not very different, but it is, right? So you would need to, these would need to change according to the horizon frame estimation, the commander and the stabilizer. You would need to use the Qdrone 2 version, not the Qdrone 1. But then in here, it's very similar. So in here, you would select another target. Because the Qdrone 1 is not using the same. So right, Quark Linux 664 was for Qdrone 1. But if you're using
Yeah.
the Qdrone 2, then you need to go here. And oh, and then you need to set your TCP/IP max file argument. And then in here, we need to change your physical plant. So, I mean, there is some work here. So in here, you need to change this Qdrone. Actually, the best thing would be, to be honest with you, the best thing would be to take the Qdrone 2. I would go grab actually a stabilizer from this. This is for the Qdrone 2 already, right? So you could take this and just copy this over here. That would be easier.
Yeah.
So that's kind of what you would need to do. But at the end of the day, if you're not, we are planning on releasing this. So if you can wait a bit, then it might be better. If you want to go ahead, I'm showing you a bit how to do this. If you really need to run it and it's not released yet, then reach out to us and we'll help you out. But it would be better if you just wait for the release. Again, make sure you're comfortable with running a single drone using a Qbot 3 by itself. Then you can kind of go from there, right? Running the multiple drones together, you could probably do that on your own.
I think the to control procedures for the Q-boards, Q-drone, and Q-car are all the same.
Very similar. Yes, you're right. Very, very similar. The more you use each of those devices, the more, after a while, it's like second nature. Yeah.
Yeah.
As you use these systems more and more, you'll gain more experience, and then you'll find out how to do a lot of stuff on your own for sure. Any other questions, guys?
No, I think.
Okay. I think this brings us to the end. It's I guess it's what, 5:10 p.m.
Yeah, 5:10 p.m.
A bit after 5, yeah. Okay.
I have a question. How can we simulate sensor fault? Control of Q-drone with sensor fault or actuator fault? How can we model this?
That's pretty specific, but again, I think you need to actually look at the models in more detail. Let me show you an example of how you could do that. If we go back to QDrone 2, let's look at the position control, okay?
Yes.
And you look at the drone stack. So here is your controller that we've been using, right? So if I go in here and I go to QDrone 2 DAC in here, this is where you have access to all the different sensors, right?
Yes.
So in here, if you want to simulate a sensor fault, what you would need to do is, for example, if you want if you wanted the IMU to fail, for example, then what you could do is add a manual switch in here. And then set this to 000. Actually, sorry, it'd be 6 zeros because you have gyroscope and acceleration data. So it's actually 6 vectors here. So in here would be no IMU, 0 measurement. This would be your sensor fault simulation. So you run this model as is, everything's flying, and then you could flick the switch on, and then it would simulate a sensor fault. And then you have your controller to identify that and do some kind of action based on that. But that's an example of how you do it, right?
Yes.
Miss, do we have virtual environment for the drone as well, like we had for the car, Q car?
No, there's no, we don't yet have that for the drone.
Okay.
We have like a simulation of a drone, but it doesn't have visualization, but it's not released.
Actually, he bring a very interesting question about the sensor or actuator fault. So, it would be too much risky to test on the physical drone. So it would be much feasible if we have some simulator where we can check it. Just like we have gazebo simulator.
We do have a simulation, like we do have a simulation that's based on like a dynamic model of the drone,
Yeah,
but
yeah.
it's not finalized yet.
Okay.
If you want, I can send you what we have, but it's not documented, and you can try to use that. Maybe that might help you.
Yeah, yeah, that would be great. That would be great.
Okay, let's start off with that.
At least we have some plant model. Right now we have just hardware in the loop. So
What's that?
I say that then at least we will have some plant model. Right now we have hardware in the loop. We do not have the plant, right?
Yeah. Okay. I'll send that to so your email address is your Mohammed Ali?
Yeah, Muhammad Qaisar.
Okay. Great. I'll send it to you and Raheem. I'll
Fine.
send you that. I'll send you the simulator of the Q-Drone 2. Again, it's not released, but I think you guys should be able to get by. The Qbot 3 resources.
Okay, I'm sending you another email as well. Kindly include that
Hi, Mitch.
email.
Yeah.
Mitch actually is responsible for this lab. Just in chat, he is typing his email ID. So whatever the documents you're sending, so keep him in also. Okay.
So, if you can.
Yeah.
I didn't quite get that actually.
Oh, Dr. Siddiq, he is the responsible for this lab. Okay.
Yeah.
So we just he is typing his email ID in chat. Okay. So even recording and whatever the documents you're sending, just keep him in CC. Okay.
Okay, email to. Okay.
Now
Yeah, I got his
put
email
in
address here. Yeah. So you want me to email you the video recordings, Qbot
Yes.
3 resources,
Yeah.
simulator to you, Raheem, Mohammed, and Professor
Siddiq.
Yeah.
Siddiq.
Yeah.
Huh, it's a nice name. Okay. No problem. I can do that.
Thank you.
Okay.
Okay.
Yeah, I'll do this after this call. Anything else? By the way, actually, we have a professor and very good friend of ours, actually, Yumin Zhang, who's definitely like an expert for fault tolerance control, and he's done a lot of stuff with all autonomous vehicles. Like even before the Q-Drone, he's done all kinds of cool stuff.
Could you please spell his name?
Yumin Zhang?
Yeah, he has a YouTube channel as well, probably. Canada professor in Canada. I have
You mean
seen.
spell the name, please.
I will
He's in-
tell you.
Okay.
He's in Concordia University.
Korea.
Concordia University, yeah.
Yeah, Concordia. Yeah, correct. Yeah.
Yo Minzan.
He has done a lot of interesting work.
Yeah. Oh yeah, he's amazing. Yeah. I mean, I don't even know the half of it, of everything he's done, but some of my colleagues know him better than me, and no, yeah, he's done a lot of great work.
He's using a lot of Quanser stuff, the Q boards.
Yeah, and
and
he's
Q car.
he's even done stuff like you're asking about, like sensor faults in simulation, but he did it hardware wise.
Yeah, he did. Yeah.
So he
Actually,
did like the actual big the full thing, you know, like a failure with the trigger with a joystick, like cutting out a prop. But then he had like I think he did some hardware modifications to our older model, and yeah, no, he's done a lot of stuff.
it was quite interesting video. I have watched his videos. Even think.
Oh, you've seen his videos. I see.
Yeah. I have seen this video as well where the actuator fault was introduced.
Okay.
Yes.
All right. Anything else, guys?
I think that's all for today.
Yeah.
Okay.
Uh, i- is it possible to optimize the battery power, because there are a lot of publications on minimization of the power consumption of quadroto
Yeah, this guy.
theoretically, but I don't know if it is possible to implement it in practice.
I would need to know how they did it in theory. It's a pretty general question. Like, I don't know what I would need to look at the paper and the theory. You need to give me a bit more information, and then you could look at. I mean, you look at this, and maybe you don't need all the sensors you're reading, right? You could just minimize the amount of sensors you're reading. You could minimize the control effort, maybe. So I don't know. These are just ideas, but at the end of the day, I would need to look at the reference paper in order to answer that question.
Okay.
But I think I've shown you you can modify all these examples, right? So if once you get to use this and know more about the inner lining of the CIMIC models, and you know that you can modify them now, then you can look at how this publication did try to minimize energy consumption, and then you can look at these models, and it should be fairly evident whether you can implement that. Probably you can. I mean, you have full control. You have full low-level control over all the sensors and actuators here. So it's very likely you'll be able to implement that algorithm to minimize power consumption.
Okay, thank you.
Yeah, it's good. Interesting. These are made for research, guys. So I mean, that's why they're all open architecture. So yeah, at the end of the day, you have very low level access. You could design your own custom control from scratch if you even want to do. So it's very this is catered for research and high level teaching. Any other questions?
No question. No, I think we have no question. No question from us.
Okay. Well, I mean, you guys look very comfortable with the system, so I think you're well on your way. If you do have any questions, please don't be shy. Send me an email, and we'll do our best to help you. And best of luck. But you look very comfortable with the system.
Thank you very much. Thank you for your time.
No, thank you. I'm
Good
glad.
time with you.
Okay. Well, great, guys. It's been a pleasure.
Thank you.
Keep in touch.
Sure.
See you, Raheem.
See you.
Yeah, thank you
Bye.
very much.